Yeah. So hello everyone. Welcome to the second part of my talk. Let's speak a bit about lower bound, what efficiency lower. So the best one function-based PRG is field length n cube, and makes this number of course one cube equal to f, which in most sense is highly inefficient and not satisfying. And the question is, can we do better? Okay? And what does it mean? Can we do better? I mean, positive answer is clear. What is the negative answer? So the way we're going to answer it, negative answer is about bounds on black box reductions. And what is black box reduction? Let's start what reductions are. Reduction is what we did now. We want to construct, starting for any efficient f, we want to construct G, pseudo-random generator G, such that we have a security proof. If G is broken, then f is not one way. That's basically what we did before. But the problem is it's too general to refute. Again, our goal now, because we failed to give better construction, our goal to prove there is no such construction or reduction, and this is too general to try. So rather we do, starting from Biliato and Rudish in 91, we refute the existence of black box reductions. Okay, these are restricted type of reduction. This says the following. First, the construction is an algorithm, G, efficient algorithm G, that make oracle use to f. Oracle use means that it treated f as an oracle. It gives queries and get back the answer. It doesn't assume anything about the internal construction of f. And the proof is also efficient algorithm, we call it R, such that give me any given oracle access to f and to any adversary that breaks the pseudo-random generator, distinguishes pseudo-random generator from random, he manages to invert f. Okay? So this is what's called black box reduction. Note that G and R should work for any, even inefficient f on A. Okay? Well, we ask them a lot. Even, actually, this is what we're going to do. They should work, namely, the reduction should invert f, even if f and the adversary are inefficient. You can criticize that for good reason, but this is what we can do. Okay, so again, it's not the most general lower bound, but it's very satisfying lower bound in the sense it is very rare that we overcome this kind of law, if at all. And specifically, let's discuss one such lower bound by Gennaro and Trevisan, very beautiful result, showing that a length double in PRG, namely PRG that double input, makes almost linear calls to f. And this actually even holds for one-word permutation. And if you start from one-word permutation, you get a PRG using a single call to f. And still, if you want to double your input, you have to make linear number of calls. Okay? So the statement is clear. This is what I want to say. I want to refute the existence of such construction of length double PRG that make less than n over log n number of calls. But we start with a different task, which is proving that random permutation are exponentially hard to invert. Okay? It was known from early 90s, but I'm going to present the proof for Gennaro Trevisan, which is inspired by, again, by Yahoo from the 80s, which is just beautiful and nice to know. So what this want to prove with high probability over random permutation f from n bit to n bit, an adversary that make less than 2 to the n queries invert f with very, very small probability, exponentially small. Okay, this is what I want to. Okay, again, it was proved using what's called lazy sampling, but this is a different proof and very beautiful. So let's do it. So assume A makes no f calls at all. Okay, it doesn't make any f calls. Right, the adversary trying to invert it doesn't make f calls. And how many permutation A inverts with probability 1? Again, you have an adversary making no f calls and it inverts f with probability 1. How many f it can invert? 1. Why 1?
Just don't put a particular answer always.
Again?
Just always say all zeros.
No, why it invert? Maybe it invert different permutation. How many permutation? I give you an A. I tell you it invert some permutation with probability 1. And it doesn't make any call to f. How many permutation can invert probability 1? And the answer is 1. Why 1? Because basically A determines f minus 1 and therefore determines f. right? If you look at F, you give me Y, you give me a primitive Y, you give me different Y, you give me the primitive different Y. So basically A is F minus 1. Okay, so determine F. If algorithm there's only single permutation, it invert probability 1. Yes?
Just to make sure, do you allow pre-processing?
No pre-processing at all. Okay, very simple setting, no problems. So I say if A invert F with probability 1, it inverts only one F. So if you choose F at random, the probability to invert it, it's tiny, 1 over the number of permutation. How many F's algorithm A inverts with probability significantly larger than exponential small? Not that many. Why not that many? It doesn't determine F minus 1, but it partially determines F minus 1. And there's not too many permutation, it can partially determine. Okay, so for the same reason, it cannot, if it makes no query, then any adversary that doesn't make query, if he does significantly better than exponential small, it only does it for very few permutations. Okay. And actually the same proof goes along even if A is allowed to make the proof to F, as long as it doesn't make too many queries. Okay? The high order bit is if A, because we are dealing with information theoretic creature, at least for a random permutation, a random function, if you do too good than the trivial one, you get a short description of the object. And short description, there's no many objects for which there is a short description. Again, it's very high level. I just want to push the idea that proving things, first this beautiful point of view or proofs, and then the proving thing in information theoretic settings, sometimes it's much easier than in computation. This is why we moved there to black box simplification. Okay, great. So now we're going to use this result to prove that length double in PRG makes a lot of calls to F. So consider the following function. It's concatenation, so let's call it G, it's concatenation of random permutation from omega of log n bits to omega of log n bits, right? It has two inputs, and for the first part, it does imply random permutation, and the first part is the identity. Okay, so it's a random permutation of few bits, and then the rest is just copy them to the output. And I claim that this function is one way, with high probability over G, for this so I confused, with high probability over G, I mean, it's like to be over F, with high probability over F, the probability that an algorithm doesn't make many queries inverted is very small. And why is that? Because inverting F is exponential hard. Now the input of length is only omega of log n, but this suffices because exponential omega of log n is super polynomial. Okay? So again, the bottom line is that as far as you care, as you know about the world, a random permutation might be one way, even though it's the identity of most of its bits. Only on omega log n bits something interesting happened. On the rest of it, that's the identity. Okay? Good? So now let's assume there is a length double in PRG that makes few number of efforts. Okay? And consider G prime that rather than calling G, okay, rather than calling, sorry, I'm confused, number of G call, rather than calling G, it emulates the call to G. Because what is the call to G? The first part, because G is a random function or permutation of this type, the first omega of log n bits going to be random value, right? And the others going to be fixed, right? So that's the identity function. So you can emulate it. Every time G makes a call to choose a different name, every time big G make a call to the little g, rather than calling to the little g, sample its output by yourself. Where do you get the randomness from? From the input. So you increase your input. For each of the call, you get another omega of log n bits. Every time G makes a call to little g, you take this part, the right part of the input, and give it the answer of G. So effectively, you emulate the call to G without calling G at all. So we have this, I don't know what to say about it, this function that stretches its input. Is it a PRG? I don't know, but it's clearly not a PRG against unbounded algorithm that makes no calls, right? suffices to P is equal to NP, but definitely a unbounded algorithm suffices. So we have a function that increases its input, and therefore computational bounded creature can tell whether it can tell it from uniform string. That's, you know, it can compute the support. Computational bounded creature can tell whether the output is in the support of G or not in the support. Okay? Good. So now I claim that D also tell the original generator from uniform string. Why is that? Because from his point of view, there's no difference if you really call the random permutation, because D itself doesn't call the permutation. There's no difference whether the generator called the pseudo-random permutation or use this input. The random permutation uses input. So it's exactly the same distribution. So now D tell the generator, the assumed generator from uniform. And therefore the reduction should invert G, right? This is what the black box theorem tells you. Give me an adversary, regardless if it's efficient or not, that breaks the PRG. I can use it using polynomial number of calls to invert G. But this reduction, because D itself doesn't make calls to G at all, and R makes polynomial number of queries, this reduction makes only polynomial number of queries to G. But we said that G is one way against polynomial number of queries adversary. Okay? That's all. We reach a contradiction. So again, one second answer. We started with the assumed generator. Because it doesn't make a lot of calls, you can emulate it using a generator that still threatens its input and makes no call at all, and this leads to contradiction. Yeah, questions?
It is a little low at my log n curve.
Hmm?
Like,
This one?
yeah.
Because it doesn't make like little of n over log n calls, when the price you pay for emulating this call is less than n bits. Okay, it makes few number of calls, and for each call you pay omega, a bit cheating of the omega, but
The point is the omega and little o together.
cancel each other, yes.
Because of-
Omega o little o of n over log calls time omega of log n bits that you pay per call is less than n. So overall, the input length you need to emulate G is less than n, and therefore it increases its input, and therefore it can be distinguished from random. Yes.
I'm probably saying something stupid here, but so G, you're saying G being one way implies that with high probability it's secure against a polyquery adversary.
Yes.
The definition of one way just talks about being secure against efficient adversaries.
Right.
And
But pseudo-random generator, what we care about in this world, we don't care about the running time. We only care about the query complexity. Okay.
Right.
But anyhow, this is true. I mean, it is true that it's also one way against efficient adversary, but also against polyquery, because when we proved before, if you remember, we say random permutation how to invert, even if we didn't care about your running time, only about the number of queries. So we proved something stronger.
Yeah, thanks.
Okay. Yeah, that's all. This is about this construction. Okay. This black box impossibility result. There are others. For instance, Ollenstein and Singa, I think. It's too small. Yeah. No. Ollenstein and Singa, sorry if I pronounce his name badly, show that any PRG makes this number of calls. Even if it only increases output by 1 bit, this is not true for one permutation, but this is true for unknown regular one function. So if you use one function, you need to make this number of calls. And Chen, Goose, Vedan, and Zhang prove that the most important, because number of calls is not that important, less important these days. What we care about more is the seed length. And we try to tackle this more important question. And they proved the matching lower bound, but were very, very restricted type of constructions. Okay, we weren't able, it's a great of a question, weren't able to give black box impossibility result that matches the n cube for any black box construction, also very restricted type of construction. And there are many, many other black box lower bound on many constructions and more, and many, many open questions. Maybe the most annoying open questions that we have for black box reduction is of weak one function. Okay? So what is a weak one function? Weak one function is a very natural definition. A function f is weak if not any adversary cannot invert it, fully invert it. Maybe it inverted it with very high probability, but efficient adversary doesn't invert it probability 1. It's a delta far from 1. Okay? It's the natural definition of weak one function. And the question is, can we construct one function out of f? And Yao answered it. You answer many things. You can, if you use independent inputs and invoke f on all of the input, or concatenate the result, then you get a one function. Okay? Fundamental result from the beginning of theoretical cryptography. But the problem is that you really have to repeat it a lot. Let's give you an example. If the function, the weak one function, was from 100 bit to 100 bit, and it was 1/1000 weak, okay? Now your final one function is on 10 to the 5th input. And now if you take a pseudo-random generator, it's going to be 10 to the 15th. It's totally useless, okay? In many settings. So the question is, can we do better? Those of you familiar with hardness amplification say in the cryptography, in the complexity theory sense, then you can do much better. You can use all kind of de-randomization techniques. The question, can we do the same for one function? The belief, at least my belief and others, I guess, that you cannot, but we don't know how to do it in black box. What we do know, we know the specific type of one function. If a regular, you actually can do maybe better. And there's Luca and Luca and we proved that, and Otek proved that the number of queries is tight. So we really need to make a lot of queries to amplify weak one function to strong one function. But again, we care less about the number of queries. We care about the input length. And for the input length, Bzuka, Couton, Karnako, and Rob Rabbach show very, very partial result. Basically, very partial, very restricted type of construction. Okay, so very basic construction. We know the answer. You cannot do. Believe me, I'm willing to put a bet here, but I spend too much time myself trying to tackle it.
How much quantify?
$100. Kidding, maybe more. More depends like what is the counter bet. Yeah, I mean 1 to 10. 1 to 10. Good. Very natural question. We have no. I mean, we don't have clue how to prove it. Good. So last topic of one function. Then we move to other stuff. Yeah.
For the previous one, I don't know if it's not as well studied. What about the security? Right? Because usually this result, the positive result, it only amplifies it to kind of unspecified negligible, right?
Yeah.
There is a sequence of payments.
Yeah.
I don't know.
Sorry, Evgeny, not quoting you.
This
Yeah.
is more important, but I don't know.
Why is it more important?
Well, because I don't know, like what is unspecified negligible? You cannot even amplify it to a fixed negligible amount.
Right. So
Quantify.
right. So you're very right. We don't know even if you can. Actually, you have partial result to show you cannot. Right here, you gave us a good answer. Maybe you don't want to amplify only to negligible. You want to amplify to say exponential small. You're willing to repeat more times, and then you expect to get way better one function. Actually, again, you have at least partial result to show you cannot. Okay. It doesn't go beyond a specific barrier, arbitrary barrier. Good. Last topic of one function. I said that one function are necessary for cryptography, at least for most cryptography. In what sense? That in most cryptography primitive, there's a hidden one function. For instance, what is the one function in PRG? Okay. What is the PRG? What is the one function there? What is the hidden? I'm asking, it's a question. The G itself, the function itself. G is it's easy to see that if you can invert G, you can break the PRG. Okay? Okay, more complicated. What is the one function in commitment scheme, in key agreement, oblivious transfer? Okay? So it turns out all this primitive boils down to the following question. You're getting two efficient functions, which are statistically far, but computationally indistinguishable. Okay? And what is the one function in there? Okay? Assume that I give it to you, G1 and G0 and G1, and tell what is the one function. They're statistically far, computationally indistinguishable. So what is the one function there?
Are they efficiently sampleable or not?
Efficiently sampleable, yes. Sorry, I was out of room. Yeah. So the one function is just not really. G, they take X and B, and if B is 0, it output G. So if B is 1, it output G1 of X, and if B is 2, it output G2 of X. Okay, this efficient computable function, since G1 and G2 are efficient. And is it true that if it's not one function, then you can distinguish between G1 and G2? So not really, because if you have the same support, if you have separate support, you take the output, you invert, and then you find out whether it's coming from G1 or G2. But if you have the same support, then the answer is useless. Okay, maybe always answer G1, 1. I mean, the input always going to be X and 1, even though it comes from G2, because we have the same support. They're statistically far, but have the same support. Okay? So facing this question, this problem, Imperial and Luby prove the following. For every function f, efficient function f, there exists a second function, f prime, such that if f prime is not one way, then you can invert f in a very strong set. Not only you can find a pre-image, you can find a random pre-image.
I don't understand, sorry, I'm going back to
Yeah.
this. If you know that they're statistically far,
Yes.
if you're given a random element,
Yeah.
I'll check the B. So, okay.
But B might be almost 1 because they have the same support. They might have the same support, but still be statistically far.
I see what you're saying, okay.
Okay? That's the same support.
Yeah.
I mean,
So
yeah.
if the functions are not injective. The functions are not
Not injective, right? Are not injective. So again, so in Pagliazzo and we show the following. F might be give me F, I give you F prime, such that if you can invert in the standard sense F prime, actually you can invert F in a very strong sense, you can find a random pre-image. And if you find a random pre-image, this exactly allows you to tell G1 and G2 apart. Okay, exactly in the statistical distance. Okay? So this is a very nice property. If any function, if it's not a one function, there's a different function. Any function, there's a different function. If it's not one way, you can invert f prime for f a random pre-image. Saying it otherwise, if there's no one function, any efficient function, not only you can invert it, you can find a random pre-image of it. Good. What is the one function in things like coin flipping protocol? Here it gets way more complicated because they have no secrecy. So what we used in the previous example is that we break the secrecy. Okay, I mean, there was a secrecy property, and if some function is not one way, we break the secrecy. Coin flipping don't have any secrecy. Okay, the coin flipping, the protocol, the party want to agree on a common bit such that no adversary can deviate it that far. So it's not clear why, actually, in the first thought, it doesn't clear why it's even require one function. It turns out that for good reason, it's easy to come up with a protocol which are coin flipping. There's no single attacking point. You have to attack it again and again and again and again only for biasing it. And then it's not clear how to do that. And there's a second problem. When you attack the object, the distribution of the probability, the distribution of the execution changes. When it changes, it's not clear they can still invert the function. Okay, so what I'm just trying to say, that the necessity for a function, even though it's look trivial on the first look, the many primitive, it's very far from being trivial, and it's fascinating area for research. Still open questions. Okay. Good. Additional open question for one function. simpler construction, matching black box lower bound. Yes.
I didn't understand your bottom line for coin flipping. What is your take-home message about coin flipping in the previous page?
Just say there's still important open questions. That's all. We don't know. I mean, even now, these days, we only know how to, that constant bias, any constant bias, coin flipping for a function. We don't know about 1/2 means negligible bias, or not super 1 over poly, say, bias. There's still open questions there, which is nothing but trivial. Not trivial. So, additional open questions. So still, even though like 40 years of research, still we are looking for simpler construction, matching black box lower bound. There's still many, many gaps. Actually, almost everywhere there's gaps. And yeah, okay. Fine, so we've finished with one function, only like an hour and a half. Beyond one function in minicrypt, yes?
Yeah, before we move to the other topic, I wanted to ask you how much of these changes if we move from a classical to a quantum computation setting, meaning you have access to a quantum, you can make quantum queries to the oracle, do you know?
Honestly, I have no clue. Yeah, seriously. Seriously, I'm not a quantum guy. You should ask tomorrow. Okay, I don't know. I guess it's only get more complicated, but this is, I think, a valid guess, but good. So beyond one function. So, you know, the other assumptions, maybe the first one was one-way permutation, which is very useful if you have one function permutation to do pseudo-random generator, etc. But it's a bad assumption in the sense that we almost have no candidate for one permutation, if at all. We need like parameters, etc. A way better constructions, which we do have natural candidates, is injective one function. Okay, we can still do much more efficient construction, etc. But it's not a big game changer. What is a big game changer is collision-resistant hash. Okay, the assumption of a different nature give you more efficient construction. Say statistical ID commitment is very easy to do if you have a collision-resistant hash function and other constructions. It implies one function. Of course, we believe it doesn't imply by Simon. Doesn't you cannot use one function with collision-resistant hash function. Okay, and maybe lastly in this minicrypt, I would say random oracle model. I guess some of you can object. What is random oracle model to begin with? We believe the party is the oracle access to random function, and the adversaries are unbounded. Okay, and in some sense, it implies collision-resistant hash. I mean, in random, you cannot find collision in a random oracle. And clearly, but for obvious reason, it's not implied by CRH. It doesn't even have a meaning what it is. So is it so it's extremely popular. I mean, random oracle heuristic, etc. These people use it in practice. And is it in minicrypt? I don't know, but I'm saying it's a good abstraction to think what minicrypt is. Because even if you put in random oracle, the important questions remain hard. We don't know how to go from private cryptography to public cryptography using random oracle and other issues. So random oracle simplify things, accelerate, make it more efficient. But in some sense, this is almost the right definition for what is minicrypt. What is not minicrypt? What is not minicrypt? What you cannot do using random oracle. It's a good like rule of thumb for assuming what is minicrypt.
Is it in any other world? Is it in Obfuscation? Is it anywhere? What does it mean? Is it in is it?
Yeah, I don't know because it depends we define minicrypt. I would like to say minicrypt for our sake. Minicrypt is what can be implemented in the random oracle. Okay, it's not a formal statement. Okay, beyond minicrypt. Okay, so okay, so what is beyond minicrypt? What you cannot do with random oracles? Okay, many things you can, but what you cannot do. So the first result we prove, the important result proof it cannot be constructed in a random call model is key agreement. Okay, what is key agreement? It's a protocol where the parties, in the end of the day, each of the parties output a bit, and they agree with essentially probability 1. And a eavesdropper seeing only the transcript cannot guess the A's output with probability significantly larger than 1/2. He can simply only flip a bit. Okay, he has no advantage over a random bit. Good. So can we construct a key agreement from a minicrypt primitive? In particular, can you construct it from a random oracle? And in Paliata-Rudik, and then improve, make tight by Barak and Mahmoudi, show no, there's no key agreement in the random call. Okay, very non-trivial result. And it applies a no black box reduction from one function of CRH to key agreement. Okay, so minicrypt does not contain all the work. You cannot do everything with random work. Almost. Okay, this is a nice observation. I don't know if Yuval was the first to make, but at least Yuval is the one that told me this result. So there's a very natural, simple key agreement protocol. It's called Merkle puzzle. And you know that in the random oracle model, if the honest parties make L queries, an adversary has to make L square queries to break it. It can break it. It's not a key agreement in the standard sense, but there's a quadratic gap between the good guys and the bad guys. So using specialized hardware for computing SHA-256, SHA-256 is the standard computation, say, what we believe heuristic for random oracle. Here it is. It's from 2019. How many calls you can make in a second? What is your guess? 1 second on this hardware. It's 5 years old. Now you can do more. How many calls you can make in 1 second?
About a trillion, right?
Maybe 10 to the 13 is more than trillion, right? 10 to the 13 calls. What it means is that Eve it takes it in the same hardware 1 million years to break a 1 second Merkle puzzle. 1 million years to make a one. So it seems that we have a key agreement out of SHA-256. Do we? No, because Alice needs to send 100 terabytes. Okay? So the question is, maybe, so it seems that the impossibilities are not very important here. What we care about, not the number of calls, we care about communication. So maybe there's a different protocol. It does better than Merkle puzzle and still retain this quadratic gap, but its communication complexity is very small. This would be great, right? So we try to tackle it, and others try as well. We spend a lot of time. No one can tell it. He spends all his master doing that. Very hard question. We have partial result. We don't know that. We believe we believe it's tight. You cannot do better than Merkle puzzle. But then very important question. You don't know that. So apparently, as far as we know, what we know about the world, there might be key agreement with quadratic gap, which has very small communication.
Sorry, I'm not quite sure I understood your point. Can you?
Yeah. So the point is that if you only care about the number of queries, quadratic gap, given today's hardware, suffices. You can have a protocol to have security. To have security. Key agreement which is sufficiently secure. You spend a second, and the adversary has to spend 100,000 years.
But then what's the connection with
The connection is that if you use Merkle puzzle itself, that realize this gap, you have to send 100 terabytes. And therefore, the protocol is inefficient. But basically, you send all the queries, the output of the good guys. The good guys, the communication of Merkle puzzle is 100 terabytes. So it's a protocol that the gap between the number of queries, the good guy and the bad guy, suffices. But to use this protocol, you need to send 100 terabytes.
The
which,
L.
L, yeah. So you have to send like
Communication.
Is this something that? Oh, this is communication.
communication. Yeah, it has to send 100 terabytes.
But random oracle model, usually the calls are things that you compute locally.
Yeah, but then you have to send them over. Merkle puzzle, you make many calls, but then you send them over in the clear.
Oh, this specific solution.
Yes, specific Merkle puzzle. Only this specific Merkle puzzle has very bad communication. The question, can you do better than Merkle puzzle and still retain the quadratic gap? We don't know. We believe you cannot. We have no reason to believe other, but we don't know.
Do you have a reason to believe?
No. Well, always you think, I always think you cannot till you see the protocol, right? I mean, I don't know. We have partial result for natural protocol, some sense for natural protocol we have.
I have a reason to believe.
Yeah, but only for very limited type of protocol. Basically, protocol that makes all the query before the interaction starts. Okay? Like Merkle puzzle.
So the efficiency problem is that L is already very big.
Yeah, no, it's not a problem that L is big because you can make this number of queries in 1 second. The problem is that you have to send the answer to this query in the clear. and therefore the communication become huge.
Yeah, the problem is that L is big and L needs to be
To
sent.
be sent, right. The problem is not that L incur for number of calls, but the problem is that the communication, L affects the communication to be also proportional to, like.
The security is that you get L square security.
Right.
So why can't you just use a smaller L? If L already, if
Because
L,
then so you get the gap becomes smaller. I mean, this you can do it, but it's not enough.
so the adversary can break it in L squared.
In
time,
L squared,
with no communication
Right.
whatsoever. While the parties they need
Yeah.
the L
Yeah.
storage.
Yeah.
So it looks like there are two measures which you could separate: communication, which is one that is but also storage. Do you have any maybe an easier low bound if you say that if L has to be kind of streaming or whatever? It's like, so basically her storage is 100 megabytes, her communication is anything. Do you have any?
No, it's a good question, but I don't know.
In multipuzzle, you don't need storage.
Mhm.
You can do it in a streaming. You just need to find an intersection.
Okay, you send in a stream and then send you, but you need you need to retain you need to keep the input somewhere, right? Where do you keep the inputs?
Yeah, how do you
Oh,
say-
okay. Yeah.
So maybe it's like, I don't know, if you, I mean, do you think it's easy if I only restrict storage and not communication? Is it easier to prove?
We never thought about it, but it's a good question.
So
Okay.
if I have like polynomially many rounds, you have no lower bounds.
No, no. Actually, one of Japanese friends, he has a lower bound, but it's perfect key agreement, and all the queries are made in the beginning. Okay, we don't know where there's adaptive queries. The adaptive queries become really.
So the problem for your lower bounds is the adaptive.
The adaptive is the main issue. Yeah, the adaptive is the main. Even 2 rounds, if it's not adaptive, we don't know. And believe me, we spend too much time.
You spend time trying to prove negative results. So maybe there's a positive result with many, many, many rounds, adaptive.
Yeah, yeah. I don't
Did
know.
you try hard to do a
No,
positive result?
no. But now you know. All of you can. Yeah. Yeah. Good. Last topic. So what is not minicrypt? Ignore this, miserable counterexample of this quadratic gap. Okay, but minicrypt is random oracle. So what is not minicrypt? Okay, key agreement is not a minicrypt, but it's not a good definition. What is not minicrypt, right? So cannot be implemented in the random oracle is not very useful. Okay. Also, public key word is not very useful definition because it doesn't contain even key agreement. Right? There's no public key in key agreement protocol. Okay.
And it has signature scheme, which is in minicrypt.
Yeah, right. Right, good. So in minicrypt, we have a very good dichotomy, which says the following. I mentioned it before. Every function is either, not really the function, but essentially, a variant of it, is either distributed invertible, or it can be used to construct one function. So when in crypto, you have some win-win situation. Every function is either useless from cryptographic point of view, it can be inverted, you can find a random preimage, or it's as strong as implying one function. Okay? Can we have such dichotomy for non-minicrypt? Okay, this is the last topic and we want to address it. Okay, we have something that win-win situation for outside of minicrypt. Okay, so let's address it. Let's be more specific. We consider 2 parties protocol, which output a single bit output. Okay, but very general question. The parties interact, and each party output a bit, and there's also the transcript that everyone sees. Okay, and here's the question: can X and Y be correlated given T? More formally, can the mutual information in X and Y condition on T be larger than 0, or saying it in a different way, X and Y are dependent given T? Can it be? Information theoretic, it's information theoretic question. What do you think? Communication complexity class, the basic result, communication complexity? No. Given the transcript, the views of the parties is always in the product distribution. Okay, so the mutual information of the views, including the output, is always 0 given the transcript. It's a basic fact from what protocols. Okay, good. But can they be computationally correlated? So it cannot be correlated given T. Can they be computationally correlated? What does it mean even? Okay, this is a question I'm going to ask. Yeah.
So you're saying that the answer to the first question, can X and Y be correlated? You're saying that the answer
Is
is
no.
Sorry, information, having mutual information doesn't mean that it's yes, the answer.
The answer always zero. The mutual information of the views of the parties, given the transcript, is always zero, unless we have a correlation to begin with. This is not interesting. So if you look at the views of two parties after they interact and you condition on the transcript, they are in product distribution. Okay, and therefore they have no mutual information. And asking, it's true information theoretically, but we know that there's difference between the information theoretic world and the computational. And asking, can they be computationally correlated? So let's look at key agreement. We know what is key agreement. It's a protocol. Assume there's always an agreement. But still, since assume X always equal Y, and since we said they are independent given T, it means that T determines both X and Y. Because if T wouldn't determine X, that means that given X, they are in product distribution, X and Y are in product distribution, uncorrelated. So what is probability they are the same? Okay? Two random variables, but independent, are not constant. The probability the same is far from now, 1. So because we know that there's full agreement, and because they have no mutual information given the transcript, it means that T determines both X and Y. Okay? If you look strong enough about the transcript, if you're unbounded, you can find out what is the output of the party. But secrecy said, on the other hand, that for any efficient adversary, the probability he guesses he finds X is 1/2. So from his point of view, given T, X and Y look highly correlated. They are always the same and uniform. Their mutual information is 1. So what happened here? Information theoretic, they are not correlated, but computationally, they are as much as correlated as they can be. They have full mutual information given the size. Okay? Good. Can we generalize this phenomenon? And the answer that we can. Okay, but again, before going there, we noted for key agreement, there's the naturally induced settings where the two random variables are uncorrelated given the transcript. For a computational bounded point of view, they look fully correlated. So let's try to formalize it. So let's speak about let's go to the extreme, what is our uncorrelated protocols. Okay, we said the key agreement is highly correlated. Let's be more formal about what are uncorrelated protocols. So it's not a natural definition. The protocol is uncorrelated if there exists some efficient, what you call decorrelator, such as the following. So you compute the protocol on random input, you get X, T, and Y. Then the decorrelator gets T as the input, and he outputs two Boolean probability distribution, PA and PB. And then you sample independently X prime according to PA and Y prime according to PB. And finally, we are guaranteed that if you look at X, Y, and T, the real output of the protocol NT, and the output of this decorrelator NT, they are computation indistinguishable. Again, there's an algorithm, decorrelator, that can basically realize the product distribution, the actual product, the parties output in product distribution. Okay? It's not only that we're into product distribution. This is tautology. We're also in product distribution. It's an algorithm, efficient algorithm. Tell here is the product distribution. This is the product distribution. Okay? It's uncorrelated in very strong sense. And I claim that these protocols are totally useless. Why very useless? Because rather than, or cryptographically, because rather than doing the protocol itself, Alice can compute the transcript by itself, apply the decorrelator, and send the distribution to Bob. So this protocol, which is totally not interesting, you can do nothing when uncorrelated. Okay? But on the other hand, key agreement, according to this definition, is highly correlated. Why it is highly correlated? Because he has no, if you think about key agreement, I claim there is no decorrelated for key agreement. Because what value should it output? Because x should equal to y, okay, you should output values such as x prime should equal to y prime. Because in the left-hand side distribution, x always equal to y. So you must output either 0 or 1. Because either output all 0 on 1, if you output something in between, the probability that they're the same is not 1. Right? So the decorrelator has to output either 2 zeros or 2 ones. Right? But if it outputs, say, 0, it doesn't know what the real output of the key agreement. So here it's going to be uniform bit, and here it's going to be always 0. Right? It's very easy. The distinguisher can apply the decorrelator by itself. So, well, if I'm getting 0, this is distribution. If I'm getting something else, this is the real distribution. So key agreement is highly is not a decorrelated protocol. It's almost the last slide. So we have uncorrelated protocol. We define it. We don't know what to do with it. They said they're useful, not useful. We have key agreement, which is not a decorrelated protocol. And the question is, maybe there are other protocols, somewhere between. They are not decorrelated and are not key agreement. Okay, maybe we live in a world of many sorts of correlation. And the answer is, with Judd and Kobe and Eran and Ronen, no. Every efficient single bit two-party protocol is either uncorrelated, totally not useful from a cryptographic point of view, or it can be manipulated to get key agreement. It's very similar to the dichotomy of Pagliazzo and Luby. In the outside of minicrypt, you have creatures that are either not interesting or as strong as key agreement. So maybe a good name for non-minicrypt, because the part of it is key agreement, actually, key agreement crypt. Not public key, but key agreement crypt in some sense. Yeah. It's all also in a random oracle model. You can give random oracle to the party and it still holds. So as I said, random oracle doesn't change the settings. It's still a dichotomy. But there are caveats. We only know to prove it for a constant, any constant though, but constant distinguishing gap. Namely, give me delta, I can give you the correlator such that I cannot distinguish better than delta. But I cannot give in advance something which is negligibly small such that you cannot distinguish. This is a huge disadvantage of this result. And secondly, it's only old for single bit output protocol. For more bits output protocol, we don't know the result. Yes?
This decorrelator.
Yes.
And nothing happens.
No, but look, this is a good point. Decorrelator does not need to understand, you say the commitment. The decorrelator does not have to understand the real distribution. It doesn't have to break the 1F function. Very good question. It suffices, he has to output x prime, y prime, and t, such that something who looked outside cannot distinguish. Maybe x prime and y prime are not x and y. If you were all powerful, you can distinguish between the output of the decorrelator and the redistribution.
You don't even need to be all powerful. If t is f of x and x is x and y is y.
Y is what?
Just some error.
So say f of x. So output something which is not x.
But then.
Sorry. But then what you can do, good point. But then it's not single bit output protocol.
But it's some distributional.
I don't know. But it's a good point. So if it's not single bit protocol, things changes. Okay? Yes.
What about private set intersection with a single element?
Again?
What about private set intersection protocol?
Yes.
If it only has one element, then it's a single bit output. Is it uncorrelated or can you make key agreement?
I guess it's correlated because you need MPC, I guess, for this one. It probably implies key agreement, so it cannot be uncorrelated, right? I guess. Let's take it offline, okay? Good. So then it's a partial result, but extending it for many bit output or to negligible distinguishing advances be very, very
But wouldn't this argument show that you cannot extend it beyond signal bit?
that you cannot output X, Y to some extent, that you cannot output X, but maybe you can prove, I don't know, maybe you can give a different simulation. Because in some sense, it's not very interesting because the simulation only for one side, right? You are right, you are right. It's like, it's not clear what you can do. Definitely not this definition. We have even like some kind of possibility result for this definition. Then you can come up with a different, interesting classification, right? But it's a good point that I didn't think about. So the point Kabir made is that if I just sending f of x, a decorrelator cannot sample x such that it look like, efficient algorithm can compute f of x and therefore can tell whether I found x or not. And the decorrelator being efficient cannot find it. Right, a good point. But okay. More challenging question is oblivious transfer. This is the last slide. Oblivious transfer on the quantum. Okay, so oblivious transfer, all you know what it is. It's like a two-party protocol. Receiver learns one of the string held by the sender, and the sender learns which bit the receiver learned. And it's complete functionality for MPC, and probably the most important protocol, right? This is deep. If there's one protocol which you care about, is OT, right? Rich set of the theoretical practical application. And can we find dichotomy for OT, even for single bit? For instance, every protocol is either trivial from insider point of view, namely can simulate it assuming you have access to key agreement, or it implies OT. Okay, so the word will be trivial protocol, key agreement protocol, and OT protocol. Okay, and there's like a dichotomy between two of those. We don't know. Another question, we spend a lot of time trying to do it, basically because OT is so complicated. It's really complicated creature. I mean, you can construct it, you look at OT, it looks simple, but then you try to play with it, think about relaxation of OT. Man, this is really, really complicated. Okay, even for the information theoretic guys, even like where Manoj is. Manoj is still here, or he went? So Manoj has some, right, you agree with it, even for informatics theoretic guy, you don't understand OT well. I mean, they have like 0-1 rule. Even the 0-1 rule said every channel either is trivial or imply OT. We have such rule, but the construction, the way you do it, you find out a specific point in the view, and you extrapolate and you use it in a very inefficient way. You need to repeat the channel many, many times till you get the same view twice. So there's no nice, say, amplification result like you have for key agreement protocol, with amplification only use the designated output of the protocol. It's really, really oblivious transfer. It look like simple protocol or simple functionality, but it was too complicated for me. But it's great open question to find a dichotomy for oblivious transfer. I think if only to understand oblivious transfer better, even without dichotomy, sufficiently interesting. That's all. So what foundation cryptography is about, I think, deeply understanding the fundamental primitives and concepts. This is what it is about. Not necessarily one function in any regime, but historically we started for one function world. Now we have some. You have others. Many people understand deep things about other stuff, but still much to do. And many exciting questions are still open in all of these worlds for you guys. Thank you. More questions?
One general question about the whole class of key agreement protocols that you have these results in. Do you always assume that Eve is a passive adversary?
Yeah, good question. Yeah. We assume Eve is passive. I guess you could ask the same question where Eve non-passive, what dichotomy? Yeah. Okay. Yeah, it's complicated enough also in Eve is passive, but it's a good question.
Just think how it relates
to
K4.
Yeah.
And there you need a public discussion about it.
Yeah, clearly. Right? No, thank you.
Let's go back to two.
So what?